So at the outset, I would also like to thank the organizers for organizing this wonderful meeting and also for inviting me here. I've already been here for a week and it's been really nice. Okay, so today I'll talk about something that we did recently on a Floquet version of this PXP model. And you can actually, okay, so the main story here is that we can actually take a slightly generalized version of the PXP model and show something interesting, which is the collapse and revival of quantum many-body scars using this Floquet structure. So, first, before I start, here is a list of my collaborators. So Bhaskar and Saurabh, they were graduate students in our department. Saurabh has since moved to IIT Bombay as a postdoc, and he's in the audience. And Bhaskar will soon move for his postdoc to China. And my other collaborators are Krishnendu Sengupta, who was here last week, and Deeptiman Sen from ISC Bangalore, who's also here in the audience. And this is the preprint of our work here. Okay, so here is the outline of the talk. So, okay, so basically first I'll discuss, so I'll actually go reasonably fast over this because from last week and also in the morning from Dr. Sugira's talk, there'll be some repetition, but I still think that it's useful to hear some things twice, okay? So first I'll briefly discuss ergodicity and its breakdown in closed quantum systems, and that was really the part of the discussion over the last few days here in this conference. And then I'll very briefly introduce this experimental realization of weak ergodicity breaking in this Rydberg chain system. So this was an experiment done in 2017, and it generated a lot of interest in this field. And while trying to understand this thing theoretically, people came up to this PXP model, which you heard about in the morning. And there's this really interesting thing called quantum many-body scarring. Okay, so that's the introduction. Then I'll come to the second part, which is our own work, where I'll actually introduce a Floquet version of the PXP model. And this Floquet version has the advantage that this can be easily realized in this existing experimental setup. Okay, so that's the advantage. And then I'll discuss how you can go about understanding the Floquet version of this problem and the role of quantum scars in Floquet dynamics. And the really new thing that comes out from here is the following, that, okay, in a periodically driven system, there's this extra knob that you have, which is the driving frequency of your external periodic drive. And what I'll show is by tuning that driving frequency, you can actually have reentrant phase transitions, several phase transitions between non-ergodic and ergodic regimes. So the non-ergodic regime is familiar from this quench problem in the PXP model, where certain simple initial states sort of never equilibrate or equilibrate much slower than most other initial states. However, as you actually tune these frequencies, you can actually tune your system from the non-ergodic to the ergodic regime, and in the ergodic regime, everything thermalizes extremely fast, and then you tune your frequency again, and you go to the non-ergodic thing, and so on and so forth. So I guess this is the first such example in a clean, disorder-free quantum system where, as a function of driving frequency, you actually see multiple reentrant transitions like this. Okay? So this is going to be basically the outline of the talk. And at any point, if something is unclear, you feel free to stop me, and I'll try to make that clear. Okay? Okay, good. So here's the introduction. So, okay. So basically, we are trying to understand the question of thermalization in isolated many-body quantum systems. So imagine for concreteness that you have, let's say, a spin model, a many-body spin model, and the dynamics is purely unitary, so there is no external heat path attached to the system. And then let's imagine that I'm concerned with some local properties of the system. Maybe I'm concerned with a single spin or a two spin or a three spin correlation function, right? Then let's say I start with a simple wave function, and we have already learned what simple means here from last week. So in the context of this talk, it just means simple unentangled initial states, okay? So let's say I start with some state like this, and actually I evolve it with this many-body Hamiltonian. Then the remarkable thing is that if you then look at a local property, then even though the wave function is always pure, because it's a purely unitary dynamics, Nonetheless, after a certain amount of time, the local properties of this pure wave function becomes indistinguishable from a thermal density matrix, okay? And that's, for example, this number. And the temperature of that thermal density matrix is just set up by the initial energy density of your starting configuration. Okay? So that's this idea of thermalization in a closed quantum system. Good. So of course, the nice thing is the reason there is so much excitement in this field is that this has also been realized in experiments over the last few years by great advancements in ultra-cold atoms and many other systems where people can really do these things in a controlled setup. So just to give you one example from this experiment, so I've taken this figure from the archive version of this paper. So basically, this is a system of rather strongly interacting bosons in one dimension. And the initial state that these guys prepare is actually, if you wish, a density wave. So in terms of bosons, you can imagine the state to be 1, 0, 1, 0, 1, 0, and so on. And then they let it evolve with the full many-body Hamiltonian. Now, you can clearly appreciate that at the thermal equilibrium, if the system goes to the thermal equilibrium, at least the system should then relax to some... it's some Hubbard model, boson Hubbard model. Okay? Right. It's an interacting Hubbard model. That's the main thing. Okay. And so then when you time involve this, what you expect is that this density wave should relax, and it should relax to some system, to some state, which has translational invariance. Okay? And that's exactly what these guys see in their experiments. So they monitor the density at the odd sites where initially it was 0, because that's what your initial density was. And then you'll quickly see that it relaxes to 0.5, which is what you expect. And this relaxation happens rather fast. It's basically some few order 1 time scales in the microscopic scales of the problem. Okay, good. We'll soon see that there's another system where if you start with exactly this kind of a density wave, it does not relax. Okay? Right. And of course, we have learned from last week that the reason this happens, the reason you expect this generic thermalization, even though there is no heat path, is due to this thing called the eigenstate thermalization hypothesis, which crucially depends on the entanglement properties of high energy states of local Hamiltonians. So the basic idea is that you prepare your simple initial state and you expand it in the eigenbasis of your local Hamiltonian, and then most of these guys, these EIs are your eigenstates of H. Most of these guys are high energy eigenstates. They are not like close to the ground state or something like that, where the properties are completely different. Then, because they are these high energy ground states, actually there's a lot of simplification because the matrix elements, both the diagonal matrix elements and the off-diagonal matrix elements of such eigenstates actually satisfy this thing called ETH, and then actually that ensures that such a relaxation happens generically. Okay? So that's the broad picture. Sorry, what? How? I mean, that's the expectation for a generic many-body system. So, I mean, for example, if you look at this diagonal thing, then this expectation value is basically the microcanonical answer if you take a high-energy excited state, and there's also a version for the off-diagonal matrix elements. And of course, for details, I refer you to these papers, and you can check the exact expressions. Okay, good. But the idea here is that okay, there is ETH, and therefore these kinds of things happen. Okay. Then, of course, we can ask what are the cases where there are these violations of ETH, right? And that's going to be. This was also briefly discussed in the previous talk. So, of course, as we have learned during the course of this meeting, at least 2 systems show violations to ETH. One is this integrable systems, which are fine-tuned systems. And the other are these many-body localized systems, which are the interacting versions of the Anderson insulator problem. Okay, so what actually happens here is that in both these systems, or in both these situations, there are an extensive number of conservation laws which emerge. And then basically if you start with a initial condition and you let it evolve, even at long time, the system retains a very large amount of memory about the initial condition, right? So in that sense, this paradigm of thermalization is violated. Okay, okay. And as I just said, these examples show strong violation of. Now the question is, this is fine-tuned and this is disordered, then you can naturally ask the question, what about translationally invariant non-integrable systems? Okay, and that's what is, that will be the focus in this talk, okay? So very recently people have realized, recently meaning in the last basically 3 years or so, or 2 years, very recently people have realized that there is actually weak ergodicity breaking in certain many-body quantum systems due to something called these many-body scars, okay? So what are these many-body scars? These are some very peculiar non-thermal eigenstates that are present in an otherwise thermal spectrum, okay? And now from the work in the previous 2 years by several groups, I've just cited a few papers here, there are several examples where people know that such states exist. For example, 1D AKLT models, where in fact one can analytically show that such states exist even in the thermodynamic limit. And the PXP model that we heard about in the morning today, where again, at least people can show that there are a few states perfectly analytically in the thermodynamic limit, and in fact, there are a much larger number of states which they observe through numerical studies, but there's a proof for a certain restricted class of states in this PXP model. One historical point, there was actually a model there was a Bose-Hubbard model in a tilted electric field, which was considered long back by Sachdev, Sengupta, and Gerwin. And basically, one particular limit of that model, deep in the Mott insulator phase, is exactly this PXP model. It's exactly the same. So this is good to remember. So their work was in 2002, but of course, at that time, nobody was worried about these things called ETH and thermalization and things like that, right? Okay, good. Okay, so what was this experiment which sparked people's interest? So this experiment was again on a, as was introduced, on a chain of Rydberg atoms. And basically what they observed is, in the experiments, they could, of course, construct certain simple initial conditions, right? So they constructed those simple initial conditions and then they let the system evolve. What they saw was most initial conditions quickly thermalized, as is the generic expectation, but few initial conditions actually took a rather long time to thermalize. In fact, about 10 times or more longer than most other initial conditions in their experiment. So that was the puzzle. Why are some of these initial conditions taking so long to thermalize? Okay? In particular, so if you want to take the correspondence to a spin model, the down means no Rydberg excitation and the up means a Rydberg excited state. Okay, so if you start your system with a state like this, like down, 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 or in terms of the Rydberg atoms, something like 0, 0, 0, 0, 0, this system rapidly, this initial state rapidly thermalizes. Whereas if you take a density wave, exactly like the experiment that I showed you a while back, which is like a 1, 0, 1, 0, 1, 0 kind of a state, it in fact keeps on doing a many-body coherent sloshing from 1, 0, 1, 0, 1, 0 to its partner 0, 1, 0, 1, 0, 1 to its partner 1, 0, 1, 0, 1, 0, and so on with a non-trivial frequency. Okay, so clearly there is something interesting going on here, right? That's just obvious by looking at the experiments. Okay, good. So then people, of course, tried to understand what's happening here. And that led to the realization that the low energy physics in this experimental setup is described by this very interesting constraint spin model called the PXP model. And then people could show why such a thing is true. So why is this true? Oh, just before that, so just a one slide thing about these quantum scars. So, okay, actually these two pictures we saw last week, this is some picture we didn't see last week. So basically what is this? So this is just a classical billiard problem. So basically if you take this classical billiard problem, if you have perfect circular symmetry, then of course angular momentum is conserved. Then this is an integrable system. Whereas if you take some weird shape like this stadium billiard, then of course there's only one conservation law here, which is energy, and therefore it's a chaotic thing. Now, the quantum version of this is you just take this problem with the hard wall boundary conditions and just solve the one-body problem. So then you can show that the quantum version also has certain eigenfunctions which are highly non-uniform in space, and these were called the one-body quantum scars, and basically the landmark paper in this is this one in 1980. Good. So these PXP model is basically the many-body version of this. Okay? So what's happening here? So okay, so this is the model. Okay? This is a constrained spin model. So why is this a constrained spin model? Because the Hilbert space is constrained. So imagine so really here you have a 1D lattice with spin half degrees of freedom if you wish. Now you go to any two neighboring sites. You go to any two neighboring sites in your unconstrained or in your full Hilbert space, of course, all four states, down, down, up, down, and down, up are allowed. But here the constraint is due to the mapping from the Rydberg atoms to this particular problem. Here the constraint is that you disallow up, okay, on any two neighboring sites. So that's the constraint. So that's why it's a constrained Hilbert space. Okay? And then let's say that I try to write the simplest possible one-body off-diagonal term. Okay, so then you would imagine writing, then you would imagine writing something like sigma x. But you can easily see that sigma x would, if it acts on some side and flips a spin from up to down, it may take you out of your constrained Hilbert space. And to rectify this problem, all you need to do is add these projection operators on the neighboring two sites. And this is the definition of the projection operator. So basically, the spin flip is only allowed if the neighboring two sites are down spins, and then the middle guy can do anything. Okay, so this is the definition of the model. This is the simplest possible one-body off-diagonal term that you can write here. Okay, so this is why it's called the PXP model. But please again remember that this is exactly the same as the dipole model, which was introduced in 2002. But I'll just use the current popular nomenclature, which is PXP. Okay. Right. Good. So then if you, let's say, look at these eigenstates of this model numerically, then you see that for most of the states, ETH is satisfied. For example, if you look at something like the level statistics or something similar, you would see that there's a Wigner-Dyson distribution here, not a Poissonian distribution. Okay? However, you also see, by the way, this is the entanglement entropy of each eigenstate where half of the degrees of freedom are integrated out. So this is like the half-chain entanglement entropy. So of course, for typical high energy eigenstates, this should follow the volume law. However, you see that there are states at high energy which have anomalously low entanglement, right? So these are these states, which these guys, so this is again taken from this Nature physics paper by Abanin, Papich et al. And these guys basically number these states like this. So they're anomalously low in entanglement. And then if you look at any other local observable, then you would see that they don't satisfy ETH. They are anomalously different from what's the canonical expectation for these things. And the reason scars or lack of thermalization shows up for the Z2 state, you remember I said that it shows up when you start your initial condition with this 1, 0, 1, 0, 1, 0 state, but does not show up for 0, 0, 0, is because these states have a very high overlap with your initial Z2 state, but has a rather low overlap with most other simple initial conditions. Okay? And this persistent oscillation which people noticed in the experiments is basically coming due to this energy scale. You see that there's a very regular spacing here, right? This spacing. So the persistent oscillation just comes from this energy scale. Okay, so that's basically the physics here. And in fact, what people have numerically seen is that these scar states don't have volume law entanglement. That's clear from this picture. But if you do a more careful finite size scaling analysis, what they see is that this has a log of L entanglement. So now several works has been done, but I think it's a fair statement to say that really the general conditions that you need in an interacting many-body system to ensure that there are scars is still a bit unclear. Okay, good. And then what I would like to today discuss is the periodically driven version of this Floquet problem. And this has been said, so I'll just very quickly go through it. Now, there's a periodic problem, so the Hamiltonian, some parameter in the Hamiltonian is time dependent, and this is the time periodicity. So this capital T is the time period of your Floquet drive, and this omega d is basically the frequency that you get. And this, of course, we know can lead to interesting states, as we have heard throughout this conference. And then really the object to consider is this u of t, where this u of t is the Floquet operator for one time cycle. Because here I'm just interested in stroboscopic observations of local properties, or equivalently this Floquet Hamiltonian. Then one can ask, what's the nature of eigenstates for this Floquet Hamiltonian or this u of t? Now, it actually is true that for generic systems, they heat up to a featureless infinite temperature ensemble, but this is actually not true for this many-body localized systems and also not true for the integrable models. So then it's clearly a natural question to ask that what happens for the Floquet version of this problem, right? Because we saw that the Floquet, the PXP model is like somewhere halfway between these two things, okay? So, okay. Here, at least, I summarize the results of, the main results of what I'm going to explain in the next 14 minutes or so. So now I want to consider the Floquet version of this problem. Okay? So now, of course, I therefore need to add another term to my Hamiltonian. So remember, we had the simplest off-diagonal one-body term here. Now I just add the simplest diagonal one-body term here, which is just sigma iz. Now this is sigma iz, so I just don't need any projectors here. And sorry, by the way, whenever you have these tildes here, I forgot to explain this. Whenever I have a sigma tilde, that basically means p sigma p. So this is a shorthand for the PXP term, okay? So things with tilde means they have two projection operators on both sides, and things without tilde means they are just without the projection operator. So basically then I take a protocol where this lambda t varies as a square pulse protocol, and basically the protocol is, as I've written here, for half the cycle it's some minus lambda, and for the other half of the cycle it's some plus lambda, so it's a symmetric protocol, and then it just keeps going. So that's your Floquet problem. In particular, I'll focus on this limit, where this lambda is much, much greater than the scale w, okay? Then please note that the instantaneous Hamiltonian has no scars. Why? Because that's obvious, because if lambda is much greater than w, this Hamiltonian is just a trivial free problem and there are no scars here. But that does not mean that your Floquet Hamiltonian cannot have scars, right? In fact, we'll see that something very interesting happens. So what happens? So here is the summary of what happens. So in this regime of large lambda, as I promised to you, there's a knob called this driving frequency. So you see, suppose now you again start with your initial Z2 state which relaxes very slowly. Then and suppose you fixed your lambda to be whatever you want, let's say some number like this. Then you keep decreasing this driving frequency. What you will see is, in these white regions, this O22 is basically some density-density correlation function which can also be easily measured in experiments. In fact, yeah, it's a two-site, you look at the Rydberg atom here and you look at the Rydberg atom 2 places away from it, and that's this thing. So you see, this is the stroboscopic observation, but you see there are persistent oscillations here, right? So immediately these persistent oscillations tell you that there is no synchronization here. So the Floquet version of ETH is lost. Why? Because these are stroboscopically measured quantities. So if there is a synchronization, then anyway, there should not be these persistent oscillations, right? That's point number one. Point number two is this blue line is the infinite temperature answer that you have. And clearly the system is not going to that, right? Now you change the frequency slightly and you go to this dark region or the tip of it, then there is this precursor. This same experiment, or rather this is a theoretical calculation, but okay. The same calculation would just give you that there are these oscillations, but then they damp down and they go to the thermal answer. Then you go to the middle of this region, there's this ringing and it very quickly thermalizes, right? And then you go here again and again the persistent oscillation. Right? And then you keep tuning this omega d and this thing will keep happening back and forth, okay? Good. So that's what we are trying to understand in the rest of the talk. I hope this is clear. What's actually, yes? Width of which region? This region. This width? Yeah. So this width is very difficult to extract analytically. We just extract it numerically with some particular definition. But yeah, I can discuss it later, right? Okay, because I'm running out of time. But yeah. Here. Oh, so here I haven't shown it. If you even increase this guy, what will happen is it'll decay like this and then it'll reappear. Yeah, okay. So this is a bit tricky. So when you go near these transitions, then there are multiple frequencies involved. That's actually true. Yeah, but nonetheless, you can clearly see that there are all these transitions here. So we'll try to understand the physics of that. Yeah? Okay, good. Okay, so this is heavy duty, but anyway, I mean, not so heavy duty. It's just tedious, not heavy duty. Okay, so there is this thing called Magnus expansion. Okay, so I'll just explain things in words, right? Because, okay, so what happens is that there is this two-step protocol. So there are two ways of setting up the perturbation theory in U, and we'll see that both the ways give you analytic insights. So the first way is this. You just set up a usual high-frequency Magnus expansion, which for this square protocol, you can just use the famous Baker-Campbell-Hausdorff formula and just calculate, okay? So then, basically, the Magnus expansion gives you the following, that you can group your terms into two classes of terms. One, which I would call renormalized PXP terms, and the other, which I'll call non-PXP, okay? So here I have just defined two dimensionless parameters, gamma, which is lambda t divided by 4, and delta, which is wt divided by 4, okay? Even though I have written h bar, but because I'm a pure theorist, h bar is always 1 for me, but so I don't mention it, okay? But yeah, anyway, you can write h bar or not. Okay, good. So, okay, so now you see, why are these renormalized PXP? Because, of course, at very high frequency, it's obvious that you would just get the PXP model because it's a symmetric drive, but the fun begins as you keep on lowering the frequency. So you see, there is some coefficient here, and there are some other coefficients here, but the structure is that there is a sigma tilde x and there is a sigma tilde y. Now you remember that your initial state, which showed the slowest thermalization, was 1, 0, 1, 0, 1, 0. So that's in the sigma z. So you can just do a unitary spin rotation in the xy plane, and you can just convert it into a renormalized PXP model. So that's it. So that's a renormalized PXP, right? Now there are other terms generated by the Floquet Hamiltonian. This calculation is just still order 1 by omega d cube. And these other terms are clearly non-PXP. They are clearly non-PXP in nature, right? And as you go further and further in your perturbation theory, they will keep on getting longer and longer range. So you can see here that these terms, and these terms are clearly more long range than the PXP model. And this is a generic property of the Baker-Campbell-Hausdorff expansion or the Magnus expansion, right? They'll just keep getting longer and longer. However, what you realize is the following. In this particular limit, so my limit was lambda was much, much greater than W, if you remember. But that in terms of these dimensionless quantities just means this, that gamma is much, much greater than delta. So in this particular limit, if you just stare at each order here, so I have used different colors here because these are just at different orders. If you stare at each order here, you can easily convince yourself that the leading contribution at each order is of the order of W times lambda to the n minus 1. Okay, that's the leading piece. And the other pieces are subdominant in lambda, which is the large number here. Okay? So then, and what you can also convince yourself is that leading piece always gives you a renormalized PXP kind of a thing. Okay? So that just involves changing some variables and just doing your perturbation theory again, and you can go to much higher order here, like this. But you see, all this is just a renormalized PXP. Now, in fact, you can just resum this thing. You can just resum this thing and you get this very nice form, which is just omega sine gamma by gamma and this. So at order, so the claim is the following. At order W, you can in fact resum the entire Magnus expansion series to give you this answer. Of course, if you go to higher orders in W, then there are more and more complications, okay? So unfortunately, I'm running out of time, but if somebody is interested later, I can explain how this order W term is obtained, okay? So the first point to remember is, as I said, when you stare at the Magnus expansion in this particular limit, when the amplitude of the drive is much larger than the W, the scale of the PXP term, you can in fact resum the highest weight term of the Magnus expansion at each order, and you can get this remarkably simple answer, okay? Then in fact, what you can also show is that the next order term is order W cube. You can actually show that, okay? So that the next term is order W cube, and this is the general structure of the Floquet Hamiltonian. Okay, good. So basically, there are these non-PXP terms hidden here, and there are some other. So this is the leading part of your answer, and this is the sub-leading part of your answer. And now the rest of the story involves the competition between the renormalized PXP terms and the non-PXP terms, right? But now you can almost guess what is going to happen. You see, this is an oscillatory function, right? And of course, you know where the zeros are of this function. So clearly, when you go close to the zero, your Floquet Hamiltonian is not a dominant PXP Hamiltonian anymore. There are all these non-PXP terms floating around. So it's completely conceivable that you will thermalize. Whereas if you're far from the zeros of this function, basically you can show that this is the dominant piece and all these other crazy things are subdominant, at least by order W cube. And then basically you are still in the coherent region. That's the picture. I hope this much is clear, right? Good. Okay. And that's indeed what's happening. So if you go to the two limiting cases, the first limiting case is, of course, where your frequency scale is much, much larger than both the energy scales in your problem. There it's entirely obvious that you will get back the PXP model, right? Because this is almost like the quench limit of the problem, right? And you indeed get that, and you indeed see persistent oscillations. And as I said, this oscillation scale is really equal to this energy scale here, right? Good. Whereas if you go to the low omega d limit, where this driving frequency scale is much smaller than both the energy scales, then actually what happens is you're really in this non-PXP regime, where there are all kinds of crazy long-range interacting terms. And then, of course, there is no reason to expect that these cars survive. And in fact, what these red dots are here in this picture are states which have overlap above a certain threshold to the Z2 state. So here the threshold is taken to be 0.01. So any state which has an overlap higher than that is marked in red. So here you can see that the physics is dominated by the scars, whereas here you can see that these states are in the bulk. Okay, good. Yeah. Left two, these guys, yes. Okay, so this number is roughly 15, and this number is roughly order 1, and this frequency is 100, so it's way beyond that. Yeah, it's way beyond that. That's why I've written these inequalities here. They're strictly valid here. Okay, good. Okay. However, now comes the so there's one more thing. Now, suppose you keep on decreasing your frequency. Then what you can actually see is these persistent oscillations remain. So imagine that I am actually going like this, but I'm still far from this first transition, okay? So then what you actually see is that this persistent frequency is actually sharply decreasing here, right? And that's because many more terms are contributing in your Floquet expansion, but you can just read off this decrease from this renormalized PXP thing that I wrote down, right? So this line is actually analytically obtained, and these points are numerical. So you just look at your data and you do Fourier transform, and you just see that there is only one energy scale in your Fourier transform, and that actually matches with the scar states in your Floquet Hamiltonian. So it's reassuring that you just get the renormalized PXP model, right? Good. So this thing is basically a drive-induced control of the oscillation frequency by controlling the scar separation. And this is clearly not present in the quench analog of this problem, right? Good, because this is the quench limit, right? When this gamma is small, then this is the quench limit, but this is clearly, yeah. Okay, good. Wow. So I'm running out of time, but then, as I said, there are several frequency-induced reentrant transitions here, and this was a picture I already showed you before, and you can see the corresponding eigenstate spectrum for the U matrix here. So you see, in this thing, there are these scars. I don't know how clearly visible they are from the back. Here also there are these scars, but here and here there are no scars. So this is like a precursor to thermalization. You see some ringing in the Z2 state, and this goes. And here, of course, it's a really short thermalization timescale. Just one very quick point. Here I have these red lines here. These red lines correspond to this other state that I was talking about, the 0, 0, 0, 0. You see, here there are persistent oscillations, but this state is always thermalizing. Okay, so that's the point. This state always thermalizes, but the real thing is what happens to these Z2 and other special states. Can I take 2 more minutes? Oh, okay. Okay. Thank you. Okay. So, right. So, yeah. And here, just to go to bigger sizes, we use some symmetry properties of the Hamiltonian, but that's just a technical detail. Okay, good. So, right. So what is the, okay, and another way to actually see that there is this scarring is if you look at some quantity called the fidelity, which is nothing but the wave function overlap at, let's say, time n, where, because there's a stroboscopic time, to the initial wave function. Now, clearly in these two regions where there is oscillations, you see that the fidelity is coming back. So it's showing these persistent oscillations. But this is not expected from a many-body system because the fidelity should start from 1 by definition and should quickly just relax to 0. And that's exactly what's happening here. And here it's really fast because that's the fastest thermalization time. In fact, if you try to estimate the thermalization time from these fidelity graphs, you see this peculiar behavior of time scales here. This is the fastest thermalization time, 7.75 in some units. And then you see that the time scale is growing, and it just goes. And then, of course, after a point, it reaches infinity on our time scale, but that's the physics. Okay, good. Okay, so now, as I said, what is this PXP versus non-PXP thing? So there was an order W Hamiltonian, if you remember, and the structure of that order W Hamiltonian was just something like this. And then there was some cos gamma times some kind of a PXP and sine gamma times some other kind of a PXP, right? Okay, so this was a renormalized PXP. And then there were higher order terms, which are all non-PXP. Now, suppose I do a numerical exercise. Because this is, of course, from the result of our calculations, right? Now, suppose I try to calculate something numerically and try to see it. So I literally calculate the Floquet Hamiltonian, and I write it in a particular basis. The basis is just my spin basis, okay? Then I just mark the matrix elements, or the pair of matrix elements where I know that sigma x tilde or sigma y tilde are non-zero. So these are like my PXP locations, if you wish. And the other guys I call the non-PXP locations, right? Of course, the non-PXP terms can also generate finite matrix elements there. But anyway, from our perturbative argument, we know that they're highly suppressed. Okay? Now, this F1 is, let's say, the norm of all these PXP matrix elements. And this F2 is the norm of all the other guys. Now, you can clearly see, so we have an analytic formula for this F1. And this F1 is just this, with some normalizations here, which I've done. And that's basically just the norm of this. And this F2 within our order W theory is 0. Okay? So you can see that if you actually do the numerics for large lambdas, this dotted line is the analytic curve, which is just this function. And the large lambda values really mimic this function, right? Now you can also see that lambda equal to equal to 10 is outside this regime. You can clearly see that. Right? So there's this regime, and below that, of course, this thing starts failing, okay? But the interesting bit is the transitions happen where this F1 and F2 start becoming equal. So basically, it's this domain. And actually, Rupayan asked how these lines were computed. These lines were computed by just comparing F1s and F2s, and this region is basically when F1 is of a similar order to F2. Which means that the PXP terms or the renormalized PXP terms are of a similar order to the non-PXP terms. And that is what leads to thermalization here, and that is what leads to non-thermalization here. Here the picture is F1 is much, much greater than F2, and clearly, therefore, you would expect some kind of an oscillatory wave. So this was basically the story here. And so this is my conclusion. Sorry, I went a bit fast for some of the technical things. So the conclusion is that in this Floquet version of the PXP model, which has a nice property that it can probably be repeated in the current experiments itself, there are two things. First is the presence of several, which we can actually analytically compute. I didn't actually say this. These yellow lines are the analytic computations. There is a shift to the fastest thermalization points because of the higher order perturbations that we have ignored, but it's quite a good match. So there's a presence of several non-ergodic to ergodic regimes as a function of the driving frequency. There's a possibility of tuning this persistent oscillation timescale as a function of the drive frequencies. And as I pointed out, both these features are entirely absent in the Quen studies of the PXP model and hopefully can be tested by standard experiments using Rydberg. So I thank you for your attention.
So questions or comments? Are there any questions? Okay.
You mentioned that the time scale of thermalization in your system is essentially infinite, but is this...
Okay, good. I don't know whether that's a completely true statement. I can ask the same question even for the pure PXP model.
This is my point,
Right,
actually,
okay.
the PXP...
So the short answer to you is it's unknown. I believe that there is a long but finite time scale.
Yeah, because these energies are not precisely equally spaced.
Exactly.
Yes.
No, the second way to understand is the following. There is this notion of an approximate small Krylov space. But you see, this Krylov space is not perfect. There is a leakage to the rest of the states. So in principle, it should generate a time scale beyond which it should thermalize. But
yes,
I don't know how to estimate the time scale. And I think it's fair to say that people really don't know what's the exact mechanism.
Thank you.
Other questions or comments? Can I ask one question? Floquet Magnus expansion is known to be diverging thermodynamic mean. So I don't know if your resummation technique is justified to...
Very good. Thank you for that question. So the question was that Floquet Magnus is of course known to be a divergent series, right? Well, that is correct. But please note that when I wrote this answer or this resummation, I truncated the series to order W. Okay, so till order W, there is this answer, and that can be resummed. I'm not claiming that I can do this resummation to order W cube or higher orders and still get a convergent answer. That's the answer to your question. So here, because we are in this particular limit, many things are simple.
Are there any other questions or comments? If not, let's thank speaker again. So you